density of media, if it travels from, or if ray of light travels from higher density medium to lower density media. If a ray of light travels from higher density medium to lower density medium, it is observed that the ray deviates. It is observed that the ray deviates away from the normal, to the surface, away from the normal to the surface, drawn at the point of intersection. Drawn at the point of intersection. Density referred here is technically termed optical density. Density referred over here, technically termed optical density. Now, as we are privy to the two processes, Rishabh,
Yeah.
one is reflection, which you know everything about, right there?
Yeah. Yes, sir.
One is reflection, which we are now aware of, and we had a law as well, or we had few statements, right? We made few statements the other day. Can you recollect? Can you recollect those statements, Rishabh?
Regarding what?
They were normal. They were normal where? Normal drawn at the point of intersection, correct?
Yeah.
Point of intersection of what? Point of intersection of incident ray. Normal drawn where? Normal drawn at the point of intersection. Normal to what? Okay, normal drawn at the point of intersection, good. But normal to what? Normal to tangent. Please be very precise and read it in toto. Normal to tangent. Then you will ask tangent to what? Then you will ask tangent to what?
Yeah.
Tangent to the surface. Clear?
Yes.
Tangent to the surface. Which surface? Previously it was surface of reflection. Now we'll go beyond to surface of refraction, right? Yeah.
Yeah.
So normal drawn at the point of intersect. So normal drawn at the point of intersect. Normal to what? Normal to the surface of reflection. So we draw normal here. Clear, yeah?
Yes, sir.
Okay, normal to any surface means normal to tangent, correct, yeah?
Yes, sir.
Otherwise, it doesn't hold water. Normal to surface means what?
Yeah.
Normal to surface means normal to surface is always normal to tangent, remember.
Okay.
Normal to surface always is normal to tangent. Tangent to what? Tangent to surface. Then comes tangent to surface can be minus. If a surface is given to you, you can draw multiple tangents to it, correct? Yeah.
Yeah.
So tangent drawn at what point? Tangent drawn at point of intersection. Clear?
Yes, sir.
of intersection of what?
Incident.
Point of intersection of ray and surface. Yeah?
Yeah.
Okay. Now this is what to us, this is as you know normal, right? And we had a few statements. One was normal, incident ray, and reflected ray, right? Yeah, remember?
Yeah.
They are all to fall in a plane, correct?
Yes, sir.
They are all to lie in a plane. This was the first statement. The second being angle of incidence is equal to angle of reflection, correct?
Yeah.
Angle of incidence is equal to angle of
Reflection.
reflection, right? Yeah.
Yeah.
So they were the ones, correct? Yeah.
Yeah.
Now we are transcending reflection and going for the next attribute, which is reflection. Correct? Yeah?
Yeah.
Again, we have a surface. Look over here. Look over here, Rishabh. Again, we have a surface. This is, of course, part of larger surface. Is it okay?
Yeah.
I'm taking a very small aperture. Clear? Yeah?
Yes, sir.
So, small aperture means we can assume it to be horizontal, right?
Yeah.
Very small aperture, isn't it? So we can assume it to be horizontal, parallel to horizontal, correct?
Yeah.
Parallel to ground, correct?
Yeah.
So this is parallel to ground. And if this is parallel to ground, Rishabh, then I first ask you what medium you have taken here. So you will say the medium in which air was is marked 1. And the medium which this medium is making an interface with is marked 2. Clear?
Yeah.
Plural of medium is media, correct?
Yeah.
Plural of medium is media, correct?
Yes, sir.
So how many medium do we have over here? 2 medium, correct? So we have taken a set of media. This is first medium, this is second medium. And what we seek? We seek angle of incidence. Clear, dear?
Yeah.
We seek angle of incidence. Of course, I'll have to take a reference, right, Rishabh?
Yeah.
What is the reference over here?
North.
Normal, correct? What is the reference over here?
North.
Normal. Normal to what? You know that very well, right?
Yeah.
So this is the angle of incidence, right?
Yes, sir.
And some part of ray that we have got, a few of them are to get reflected, correct?
Yeah.
Few of them are to get reflected, and the other are to get refracted. Is it okay?
Yeah.
And the other are to get refracted. By that, what I mean, the other set will pierce into second medium. And
Yeah.
the other pair or the other rays, they are to go beyond the interface, right there.
Yes, sir.
A few of them cannot transcend the interface. So what happened? They got reflected, correct? Yeah? They
Yeah.
cannot overcome the intersection. They got reflected. Yet a few were able to transcend this barrier, correct?
Yeah.
Barrier of what? Barrier between two media, correct?
Yes, sir.
So they are able to see through this interface, thereby entering the other medium, correct?
Yeah.
And when they enter the other medium, we observe a peculiar behavior. When they enter the other medium, we observe a peculiar behavior. And what that behavior? That behavior being either the ray are to move away from normal, either the ray are to move away from normal, same normal.
Yeah.
Same normal. Normal doesn't change, reference doesn't change, right? Yeah.
Yes, sir.
So either the rays which have transcended the barrier, either they are to move or still moving away from normal, or they are towards it. Is it okay?
Yeah.
Or they are towards it. Visible?
Yes, sir.
Okay. In any case, the angle that the ray, any case be it, moving away, moving towards, be it any, the angle that the ray makes with normal is read or given an epithet of angle of
Refraction.
refraction. Yeah?
Yeah.
What is the epithet that we are using here? What
Angle
is
of
the common
refraction.
nomenclature? What are we naming it to be? We
Angle
naming it to be angle of
refraction.
refraction. Clear?
Yeah.
Then this is called angle of refraction. How is angle of incidence, I or theta as we have marked over here, how is angle of incidence related to angle of refraction? Correct, yeah?
Yeah.
Now is next we are of course to find if this is the observation. Observation doesn't come from blue, correct dear?
Yeah.
Observation has a reason to stand, correct dear?
Yes, sir.
Observation is to be read against logic, and that logic is to be decoded vis-a-vis theory or mathematics, right?
Yeah.
So we need mathematics to substantiate our observation. Only when the science diaphora is to lay credence to it, correct?
Yeah.
So if this is the observation, what goes behind this observation? What is the root cause of this observation, correct?
Yeah.
So the root cause of this observation being when light travels from one medium to the other, it deviates. It deviates.
Yeah.
It deviates from its path. Then you will say, okay, taken. But this again is no exception from observation, correct? This is what you observed. Reason it out, right, dear? You
Yeah.
will ask me for a reason. Reason it out. Why are you into observing whatever you are into observing? Reason it out, right?
Yeah.
So reason lies in
Difference in optical
reason. Yeah, true. Tell me, Rishabh.
difference in optical density.
Reason lies in, as you rightly did pontificate, difference in optical density. Reason lies in difference in optical density. This optical density is also kind of delusive. I'll say it is more than what meets the eye. Lydia,
Yeah.
it is more to it than what meets the eye. It's delusionary. Why is it delusionary? Because generally the term density was referred to material density, correct?
Yeah.
Generally, when I used to speak or whenever you have come across the term word density, you related it to mass per unit volume, right?
Yeah.
We related it to mass per unit volume. That is what is the organic meaning for
Def-
density, right here, right, Risha?
yeah.
Here we make a departure. Here we make a departure. And what that? That being, we no more refer to material density. We no more refer to
Material
material
density.
density. We refer to density which is prefaced with optical. We refer to density which is prefaced with word optical. Now, what is so optical about density? You will ask, How does it cut ice to read density vis-a-vis word optics? What is now a new term coined? Optical density. To make it generic, Rishabh, what will I say? It is not about optical density. It is more about what is the speed of a wave. What it is more about, Rishabh?
Speed
It
of
is more to do with the speed of a wave. So let us not confuse ourselves with optical density, acoustic density, and then over the top density.
yeah.
Yeah,
Yes.
more the wordings, more will be confusion to crop. Correct, yeah?
Yeah.
What we do, we nip all in the bud just by one word. And what is that to us? Speed. What is that to us? Speed. If the speed of light, if the speed of light is more in air, if the speed of light is more in air in comparison to iron, are you getting it? Are you getting it?
Yeah.
If the speed of light as measured, we can measure speed of light, right? Yeah.
Yeah.
So the speed of light, measured speed of light, mathematical measurement. If the speed of light is greater in air in comparison to iron, then air is rarer a medium for light in comparison to iron. Clear?
Yeah.
Is it okay?
Yes.
Then for light, what will you say? For light, you will say that air is rarer than iron. Clear? Clear, dear?
Yes, sir.
Now recollect an experiment which teacher did ask you not to indulge in, as you would have risked your life. Teacher asks you in seventh standard, put your ear on the rail track. You can hear sound of movement of wheels, correct?
Yeah.
Teacher told you also not to execute as you want to then risk your life, correct?
Yeah.
What this observation tells you, Rishabh, today? What are you to read off this observation? Because when you are standing on the platform, you are not able to know, rather, you are having no inkling of train's arrival at station. Correct? Yeah?
Yeah.
You are not able to hear any sound. You are not privy to where the train is. As you are not able to see, you had no inkling that train is approaching station, right?
Yeah.
But when you kept your ears on track, you were able to make that yes, the train is approaching station, correct?
Yes, sir.
How? How did you guesstimate that it is approaching? You are able to hear sound of wheels or sound of movement of wheels, correct?
As sound travels faster in solids.
And sound travels faster in solids than in
Eh,
air, correct?
yeah.
So what according to you is iron a medium to acoustic wave? I'm not saying optics now. Optics means light, and acoustic is Coustic. Acoustic. Acoustic means sound. Okay, dear?
Yeah.
Acoustic means sound. So for sound, which is rarer, iron or air?
Iron.
Iron is rarer. Why? Because sound is able to travel
Faster.
faster in iron. Are you able to know that this has got nothing to do with material density? Are you able to establish that concept? Yes or no?
Yes, sir.
So what it is only to do with? What it has got everything to do with is speed of wave. Can we say that?
Yeah.
Amorphously, it can be sound wave, it can be light wave.
Yeah.
So what are we taking amorphously? Generic equation. It is dependent on
Speed of.
speed of wave. Clear, dear?
Yes, sir.
Sure.
Yeah.
This being known to you, this is what is the meaning of optical density. Yeah,
Yes, sir.
very good. So as we move from denser medium to rarer medium, what will happen to light ray? As we move from denser medium to rarer medium, what happened to light ray? What happened to speed of light? What happened to speed of light? If you're moving to rarer medium, suppose you get a place which was crowded and all of a sudden you find it being in expanse. What will you do? You will move freely, right there?
Yeah.
It's organic for your speed to increase, correct?
Yeah.
So light also find it to be in a rarer medium. What happened to its speed? Its
Increase.
speed is to increase, correct there? Okay, so speed will increase, but frequency, remember, remains same. Clear?
Yeah.
So speed increases, no doubt about it, but frequency of wave doesn't change when it moves from one medium to the other. Remember these.
Yeah.
Okay, you'll be using them in higher grades. Clear? Yeah?
Yes, sir.
Speed will change, lambda will change, frequency remains
Same.
unchanged. Okay, so as it moves from denser to rarer, it deviates away from normal. Yeah?
Yeah.
And this is the case for which wave? This is the case for light wave or optics, correct?
Yeah.
Tell me if the same experimentation is carried with a caustic wave, what will be your observation? Same, exactly the same being carried with now a caustic wave. What will be your observation? Will it be akin to what is depicted on board,
Yes.
or you will make a departure?
It'll be the same.
So, if you are taking a caustic wave there, then as it moves from rarer to denser, it will move towards the normal. Clear, dear? Because you're talking of what density over here? Let's say one is here, the other is, I've taken denser, right? So this is denser. Let us say this is iron. Okay?
Yeah.
Let us say this is iron. And this is air, correct?
Yeah.
So what happened to speed of light?
Degree. Light or.
Well, as it moves from iron to air, speed of light will increase, correct?
Yeah.
But what will happen to speed of sound?
Decrease.
So what should be the nature?
It should move away.
Should be reverse of what light did, correct? Yeah?
Yeah.
If light is moving away, which it will, then sound or acoustic wave should move
Words.
towards, correct? Yeah?
Yeah.
Am I clear on this?
Yes, sir.
Very good. Now, right. Rishabh, as we had few statements for incident ray, normal ray, angle of incidence, angle of refraction, we do have for refracted ray as well. Is it okay?
Yeah.
And what being the first one? The first one being Incident ray, normal, reflected ray, and
Refracted.
refracted ray. Is it okay?
Yeah.
Incident ray, normal, reflected ray, and refracted ray. Correct, dear?
Yeah.
They are all to fall in a plane. They are all to lie in a plane. All lie in a plane. Yeah, dear?
Yeah.
And then we move from one medium to the other medium. And as you know, when you move from one medium to other medium, the speed of ray taken is ordained to change, correct?
Yes, sir.
So if the speed of ray taken is ordained to change, then as per Huygens principle, name of the scientist Huygens, Huygen. Is it okay?
Yeah.
Name of the scientist Huygens. So as per Huygens principle, sine I, sine of the angle of incidence, clear here?
Yeah.
Sine I upon sine R, sine I upon sine R. What is I over here, Rishabh?
Incident ray.
I is the angle of incidence,
Yeah.
correct?
Yeah.
And reference is normal, right here. Look over here, is it?
Yes, sir.
And what is R? R is the angle of
Ah,
refraction.
yeah.
Reference again, normal, right?
Yeah.
So sine I by sine R is equal to speed in second medium by speed in first medium. That means speed in the medium in which the ray is going to speed in medium from which the ray is coming. Clear?
Yeah.
Speed in medium to which the ray is going to a speed in medium from where ray is emanating. Correct, dear?
Yeah.
Or coming. Clear?
Yeah.
This is experimentally and mathematically proved statement. So we are not going into veracity of it because at this grade you are not to look for proof of it. Proof will come in 12th standard. Sin I by sin R. How and why is it? V2 by V1. Is it okay?
Yes, sir.
And we have one more relation, Risha, and that is mu2 by mu1. What is this relation to read? Mu2 by mu1. Now what is mu? What is mu a symbol for? Mu is a symbol for refractive index.
Okay.
Okay. What is mu a symbol for, Rishabh?
Refractive
Mu
end.
is a symbol for refractive index. Now I'm coining a term, new term over here. Speed was known to you, so you didn't make any protest. But here you are to sound protest, which is what is this new term, which is being named refractive index now. See, refractive index is property of a medium. Refractive index is property of any medium comes with certain integral property. And refractive index is also property of a medium. Then you are at once to ask me, property means what will it depend on? To which I am to say, how did you distinguish between two media over here? You will say that you distinguish between the media owing to different speed, correct, dear? If
Yeah.
speed is same, will you ever to distinguish between two media, dear?
No, sir.
No. So you are laying credence to differential speed, correct, dear?
Yeah.
And then I ask you, find this difference in speed you attribute to frequency or wavelength. What will you say? Different speed, okay. As you move from one to the other, speed got differentiated. Different speed you are getting. But this differential you are attributing to frequency or wavelength. F is frequency, lambda is called wavelength. Is it okay?
Yeah.
What is F called? F is called frequency. And what is lambda read?
Wave.
Lambda is read as wavelength. So what are you ascribing this change in speed to? Are you ascribing this change in speed to frequency or you are to wavelength? Come on, dear.
Wavelength.
Wavelength. Very good. So is it not from here? I'm asking, think about it. Does it not, this experimentation, did it not imply that for different medium we have different lambda?
Yeah.
The implied meaning, think about it. What
Yes.
is the implied meaning? The implied meaning being as medium changes
Wavelength.
wavelength. As medium changes
Wavelength.
wavelength. And we give it to Cauchy, Cauchy. Cauchy, the name of scientist. We give it to him for establishing a relation between mu and mu and wavelength.
Okay.
These questions are asked in KVPY examination. Mu is called refractive index. Clear?
Yeah.
What is this refractive index? A property of medium. What
Yes.
are A and B here? They are experimental constants, correct?
Yeah.
What is lambda over here?
Wavelength.
Lambda is wavelength, correct?
Yeah.
So if you take a monochromatic light, monochromatic means one wavelength. Is it okay?
Yeah.
So if you take red light, let us say, if I have taken red light, it is monochromatic. That means you will associate only one lambda with it, correct?
Yeah.
So we are associating one lambda with it. It is monochromatic light. Is it okay, Rishabh?
Yes, sir.
Very good. So monochromatic light taken, I pass this light through water. When we pass this light through water and read refractive index of water, clear?
Yeah.
What we read? We read a property of water. And that property is based on experimental observation. I'll come to the mathematical observation in a few while from now. Is it okay?
Yeah.
So we observe that mu depends on the experimental values, and we wrote mu of glass as 1 point, let's say 33. Is it okay?
Yeah.
We found that mu of glass is 1.33. Clear?
Yeah.
Will this be the mu? Will this be the mu if you change red light to orange?
No, sir.
Will the mu be same? Will the mu of glass read same if you change wavelength of experimental wave? If you have changed red light to orange light, will I read mu of glass the same?
No.
Or is mu subject to lambda? What you say, Rishabh?
It is subject to wavelength.
Good. Mu is subject to lambda. Therefore, when we say mu of glass is 1.33, it is not an absolute statement. Clear?
Yeah.
When we say mu of glass is 1.33, it is a relative statement. Generally, we take a ray which is mean ray. Mean ray in spectrum means yellow ray because yellow is nearest to white ray. Correct, yeah?
Yeah.
White, is not a color, right, yeah?
Yeah.
White is combination of 7 colors. Correct, yeah?
Yes, sir.
We don't have a frequency related to white ray. Correct, yeah?
Yeah.
What we take a frequency which is nearest to it, and that we attribute to mean ray or yellow ray. Clear?
Yeah.
Mean ray means in spectrum with your yellow is the mean. Clear, dear? Clear, dear?
Yeah.
So we take help of yellow. Whenever I'll say henceforth that refractive index of water is 4 by 3, let's say, or glass is 1.33, whatever, then you are to read it as this is a relative quantity, means what you are to read in my statement, this is refractive index owing to which ray, when the reference is taken as yellow ray. Correct, yeah?
Yeah.
Are you clear on this?
Yes, sir.
So Cauchy was the person who related refractive index with lambda. And it doesn't end over here. It goes ad nauseum. Lambda is square, then d by lambda 4, so on and so forth. And exactly this question was asked in KBB1. Okay, so this is the Cauchy relation which reveals dependence of mu and lambda or vice versa. Clear, dear?
Yeah.
So this is how mu changes with lambda. Now what is mu read to be? What is the name given or epithet given to mu?
Refract.
Refractive index. Clear, dear?
Yeah.
And what ratio mathematically? Now to the mathematical ratio, dear. Sin I by sin R. What is this to us? Similar to speed. This was V2 by V1. This
Yeah.
will be V2 by V1. Right, dear?
Yeah.
Which when multiplied, if we write it this way, mu sin I is equal to, or mu1 sin I is equal to mu2 sin R, correct?
Yes, sir.
So what we can derive from here is mu sin theta is a constant, can be
Yes, sir.
u1 sin I1, and you take another band here, take one more band, yeah? That means take one more medium, clear?
Yeah.
If you take one more medium, Rishabh, then for this medium, look over here. For this medium, if this is R, this will be R, correct?
Yeah.
So for the next interface, let me mark it 3. For the interface 2, 3, can you check it? Or can you, is it visible on the board?
Yeah.
For the interface 2, 3. What is R? Is not R the angle of incidence?
Yes, sir.
Can we say R to be the angle of incidence? Yes or no?
Yes, sir.
So R can also be marked as I2 again. If I'm marking this I1, first one as I1, then second one can be marked I2, right here.
Yeah.
What we can get to see, mu1 sin I1 is equal to, can I do it by I2?
Yeah.
An idea.
Yes, sir.
mu2 sin I2, right? And you
Yeah.
can further it, Fish. Sorry, you can further it, Rishabh. What can you further it to? Tell me. Are you there, Rishabh? Are you there?
Sir, your video is frozen and I can't hear you.
Fine now? It's fine.
Sir, I
Is it
can't.
good now?
Yeah. Fine.
Good.
Yeah.
Established, right?
Yes, sir.
Okay. Now, if this is the trend, Rishabh, if this is the trend that we are following, then we can further it to n bands.
Yeah.
So what we get to see from here, mu sine theta or mu sine I is a constant, correct?
Yeah.
Mu sine I, from where we derive mu sine I being a constant. Clear?
Yes, sir. Yes.
Idea?
Yeah.
Okay. I take the right down. Let us take, let us take two media with refractive indices. Let us take two media with refractive indices mu1 and mu2. Let us take two media with refractive indices. What did I say, Rishabh?
Mu1 and
Mu1 and mu2. So this is I, this is the other one. This is mu1 to me, this is mu2 to me, and this again is mu1. Find here.
yeah.
This is the normal. They being parallel, this line will hold good vis-a-vis normal for both the surfaces. Correct?
Yeah.
Rectangular slab, so these are parallel to each other faces. Correct?
Yeah.
Okay, let me assume mu2 being greater than mu1. Right here.
Yeah.
What happened? It will bend towards the normal, right?
Yes, sir.
And then we draw normal here at the point of incidence, correct?
Yeah.
Now it is moving from denser to rarer, right?
Yeah.
So it is to deviate away from normal, right?
Yes, sir.
Okay, dear, is it visible?
Yeah.
Now see for yourself what we get. This is I, and what will this be marked? R, visible?
Yeah.
Is it visible?
Yes, sir.
Okay, this will also be our opposite angles right here.
Yes, sir.
Okay, and what about the other angle? I'm marking this as I don't know. I'm marking this I prime. Clear?
Yeah.
Now I ask you to write equation vis-a-vis sin I, sin R relation. Is it okay?
Yeah.
This is also called Snell's law. SNE double L is the name of the scientist. Is it okay?
Yeah.
It is also called Snell's law. Snell's law. Is it okay?
Yeah.
Now tell me for first interface, what will you write? Sin I by sin R. Mu2 by mu1, right here?
Yes, sir.
And now go for the second interface. You know very well that rays can be retracted, isn't it?
Yeah.
You can retract the ray, correct? Yeah, the ray shown over here can be retracted, right?
Yes, sir.
So I'm retracting it. If I retract, look at it. Is it retracted?
Yeah.
Okay, help me write sin I, sin R for retracted rays. Sine of I prime, right, Rishabh?
Yes, sir.
Divided by sine of R, correct?
Yeah.
Is how much to us? Is mu2 by mu1, correct?
Yes, sir.
What is this to get you? What is this to get you? Tell me from here. Right of the equality mu2 by mu1. Right of the equality mu2 by mu1. Are common. Are common, right here?
Yes, sir.
So what will be your understanding on I and I prime? What relation they are ought to share?
They're equal.
They are equal. Therefore, what we can say? The ray which enters and the ray which emerges. Correct, yeah?
Yeah.
This is called incident ray and this is called emergent ray. Correct, yeah?
Yes, sir.
They are parallel to each other, right?
Yeah.
They are parallel to
Each
each
other.
other. They are parallel, but they got displaced, right? Yeah.
Yeah.
You can see for yourself, they got displaced. Clear?
Yeah.
So we'll study about this displacement in the class to come. Clear, dear?
Yes, sir.
Got today what is refraction, what are refractive indices, and what do we mean by optical density, or for that matter, how is density related to speed, right?
Yeah.
Anything which you deem as
No, sir.
good?
Yeah.
Okay. So today your task being you are to upload the questions which were found amiss.
Yeah.
Okay, the questions which were missing, the answer of the questions which were missing. Today I implore I should get them by 12 o'clock midnight, right?
Yes, sir.
Okay, without fail you are to,
Yes, sir.
or
Yeah.
you have to ask any, then ask.
No, sir. It's fine.
Sure, you will be able to get the end of all the questions on your own.
Yes, sir.
History misses here and there intermittently you have missed, I think, in totality 9 or, no, not 9, 6 or 5 questions you have missed.
Yeah.
So those you are to upload
Actually,
now.
some of them were common in HC Verma and NCRT. Some of them
Yeah,
were.
yeah. So you are through them, right?
Yeah.
This will be the order of day here. You will get common questions. This goes
Yes.
without saying. Yeah. So you will be able to upload those questions today by 12 midnight.
Yeah.
Okay. Good. Thank you. Thank you, Rishabh. Keep
Bye.
reading.
Yes, sir. Bye.